Hi everyone, it's Professor Pemberton. In this video we're going to talk about triple integrals. So in a previous section we talked about how to calculate the double integral for a function of two variables over a rectangular region in the plane. In this video we're going to talk about how to calculate the triple integral for a function of three variables, x, y, z, over a rectangular solid box in three-dimensional space. So in this video we're going to talk about how to recognize when a function of three variables is integrable over a rectangular box, and then we're going to evaluate a triple integral by expressing it as an iterated integral. So integrable functions of three variables. We're going to talk about the most simplest case for integrating a function of three variables is where we integrate over a rectangular box in three-dimensional space. Our rectangular box will be capital B. It will consist of the points x, y, z, where your x values are between A and B, including the left endpoint and the right endpoint. The y values are between C and D, including the endpoints, and then the z values are between R and S, also including the endpoints. To be able to calculate the triple integral for the function f over this rectangular box, we're going to first divide up the box into sub-boxes. And to do this, we're going to take the values for x, which are between the closed interval a to b. We're going to divide this interval up, or partition the interval up, into L subintervals of the form x sub I minus 1 to x sub I. Each of the subintervals will have equal width, which will be represented as delta x. We'll take the closed interval for the y values between c and d. We'll divide that interval up, or partition that interval up, into m subintervals, which will consist of the intervals y sub j minus 1 to y sub j. Each of these subintervals will have equal width delta y. And then finally, we'll divide the interval for the z values between r and s into n subintervals of the form z sub k minus 1 to z sub k. And each of these subintervals will have equal width delta z. So how do you calculate delta x, delta y, and delta z? Well, delta x will represent the width of each rectangular box. Delta x will be the right endpoint, which was b, subtract the left endpoint, which was a, and then we divide into L subintervals for the x values. So delta x will be b subtract a in the numerator, and then divide by L. The length of each rectangular box will be represented as delta y. This will be the right endpoint, d, subtract the left endpoint, c, and then it's all divided by m because we have m subintervals for the y values. So delta y will be d subtract c in the numerator and then divide by m. And then the height of each rectangular box will be represented as delta z. Again, it's the right endpoint for the z values, which was s, subtract the left endpoint, which was r, and that's all divided by n because we're dividing the z values up into n subintervals. So what the width, the length, and the height of each of these sub-boxes are, we can actually calculate the volume of each of these sub-boxes. Each sub-box will be represented as b sub ijk. The volume of the rectangular box, b sub ijk, will be equal to delta x times delta y times delta z. And so we're taking this rectangular box, capital B, in three-dimensional space. We are dividing this rectangular box into sub-boxes, where we're taking the x values between a and b, we're taking the y values between c and d, and then the z values are between r and s. We divide or partition the x values up into L subintervals. We divide the y values, the closed interval for the y values, into m subintervals, and then the interval for the z values into n subintervals. And then that will give us L times m times n sub-boxes. Each of those sub-boxes will be represented as b sub ijk. B sub ijk will consist of the closed interval x sub I minus 1 to x sub I, cross the closed interval for the y values, where y sub j minus 1 to y sub j, and then cross the z values. The closed intervals were from z sub k minus 1 to z sub k. Each of these sub-boxes will have a volume, which will be represented as delta v. It's the product of the width times the length times the height of each of these sub-boxes. So we can calculate the volume of each of these sub-boxes, and if we add up the volume of each of these sub-boxes, and we let the number of partitions for the x values, the y values, and the z values go to infinity, then we can form a triple Riemann sum of the form. The I values will go from 1 to L, the j values will be from 1 to m, and then the k values will be between 1 and n, and then we're going to add up f of x sub ijk star, y sub ijk star, and then z sub ijk star. Those are sample points for each rectangular box from b sub ijk. You substitute in the sample point into the function to determine its value. Then you take the value and you multiply by the change in the volume for each sub-box. So in a similar way, for double integrals, we can take the sample points to be any point that's in these sub-boxes b sub ijk. And in just in the same way as we had for double integrals, we can define a triple integral as a limit of a triple Riemann sum. The definition, triple integral of a rectangular box. The triple integral for a function of three variables, x, y, z, over a rectangular box B is defined as follows. It's a limit of a triple Riemann sum where you have a limit where L values will go to infinity, M will go to infinity, and also N will go to infinity. So the number of partitions or subintervals for the X values, the Y values, and the Z values will go to infinity. Of the triple Riemann sum that we had before, if this limit exists, then you can form a triple integral over the rectangular box B in 3 dimensions. The integrand will just become the function of 3 variables, f of x, y, z, and then delta v will become dv, the change in the volume. If this triple integral exists, then the function f is integrable over the rectangular box B, and you can calculate its value. This triple integral will always exist if the function f is continuous. However, it turns out that continuity is sufficient but not necessary. In other words, if the function f is bounded over the rectangular box B and also is continuous except possibly at the boundary points of the rectangular box, then it turns out that the function f is integrable over the rectangular box B as well. Now that we know the definition of a triple integral and when it exists, we can actually calculate its value. So just in the case for a double integral for a function f over a rectangular region, now we can have a iterated triple integral over a rectangular box. So Fubini's theorem, if f, x, y, z is continuous on a rectangular box B, which is of the form closed interval a to b for your x values, cross closed interval c to d for your y values, cross closed interval r to s for your z values, then the triple integral over the rectangular box B, the function, or the integrand f of x, y, z, with respect to v, is equal to a triple iterated integral, where your outside integral is in terms of z values, so integral from r to s corresponds to the z values. Your middle integral corresponds to the y values, so y between c and d, and then the inside integral corresponds to the x values, which are between a and b, and the integrand stays the same, f of x, y, z. Fubini's theorem states that if you are integrating over a rectangular box, and the function f is continuous on this rectangular box, then the integration can be done in any order. Just make sure that the limits of integration correspond to the variable of integration. In this case, x corresponds to the inside integral, y corresponds to the middle integral, and then z corresponds to the outside integral. To be able to find out what the value of this triple integral is, we first integrate with respect to x, where you treat y and z as constants, and x is the variable of integration. After the first integration, then you will have y and z remaining. You integrate now with respect to y, where you treat z as a constant, and then finally you'll integrate with respect to z. Fubini's theorem states that if the function is continuous over the rectangular box B, then the integration can be done in any order, and each of those orders of integration can be done in any order. Just make sure that the limits of integration match up with the integral for the variable of integration, and you'll have the same value for the triple iterated integral in all 6 cases. Example 1, evaluating a triple integral. Evaluate each of the following triple integrals. Number 1, you have a triple iterated integral where your outside integral corresponds to the z values between 0 and 1, your middle integral corresponds to y values between 2 and 4, and your inside integral corresponds to x values between -1 and 5. The integrand is x plus yz squared. Notice that the integrand is a function of 3 variables, f of x, y, z is x plus yz squared. That is the continuous function over the rectangular box B, which is of the form -1 to 5, closed interval for your x values, y values between 2 and 4, and then the z values were between 0 and 1. Fubini's theorem states that the order of integration can be done in any order and you'll have the same value over the rectangular box. So we'll integrate in the order x first, while we keep y and z constants. Then we'll integrate with respect to y, where we'll treat y as a variable and z as a constant, and then we'll finally integrate with respect to z. Let's integrate with respect to x first. So if you integrate with respect to x, x the variable, y and z are constants. The antiderivative of x will be 1/2 x squared, and the antiderivative of yz squared will be xyz squared, because y and z are constants. So you have the antiderivative. Now you evaluate using the fundamental theorem of calculus, where you evaluate at the upper limit, which is x equals 5, and you evaluate at the lower limit, x equals -1. If you substitute x equals 5 into the antiderivative for x, then you'll have 1/2 times 5 squared, which is 25 divided by 2, plus 5 times yz squared, and now subtract when you substitute in -1 into the antiderivative. So you have 1/2 times -1 squared, that'll just be 1/2, and then you'll have plus -1 times yz squared, and so that will be subtract 1/2, and then you'll have to add yz squared. Then you have dy dz, because you still have integration with respect to y and then z. Simplify the integrand as much as you can before you integrate with respect to y. So you have 25 divided by 2, subtract 1/2, that's 12. And then you have 5yz squared plus yz squared in the integrand. Keep the outside 2 integrals the same. You have integral for z on the outside from 0 to 1, and then y is now on the inside between 2 and 4. You simplify the integrand will become 12 plus 6yz squared. Now find the antiderivative with respect to y, where you treat z as a constant, and y is the variable of integration. The antiderivative of 12 is 12y, and then the antiderivative of 6yz squared is 3y squared z squared. Evaluate the antiderivative at the y value, y equals 4 for your upper limit, and the y equals 2 for your lower limit, and then keep the integral on the outside was 0 to 1 for your z values. When you substitute in y equals 4 into the antiderivative, you'll have 12 times 4 plus 3 times 4 squared times z squared, and then subtract when you substitute in the lower limit of integration using the fundamental theorem of calculus. You'll have subtract the quantity, 12 times 2 plus 3 times 2 squared times z squared. Simplify the integrand as much as you can before you integrate with respect to z. When you simplify, you'll have 24 plus 36z squared. And so you have a single integral now between z equals 0 and z equals 1 for this integrand, 24 plus 36z squared, and you integrate with respect to z. The antiderivative with respect to z is 24z plus 12z cubed. Now again, use the fundamental theorem of calculus to evaluate the antiderivative at z equals 1, which was the upper limit, and then subtract when you substitute in z equals 0 for the lower limit. And when you do this, you'll end up with the value 36 for the triple iterated integral. And so again, because of Fubini's theorem, since we're integrating function f, which is continuous over the rectangular box, x values between -1 and 5, y values between 2 and 4, and z values between 0 and 1, you could integrate in any order and you'll also get the value 36. Let's try one more. Number 2, you have the triple iterated integral. Your outside integral is between 3 pi over 2 and 2 pi. That corresponds to the y values this time. The middle integral corresponds to x values between 0 and pi, and the inside integral corresponds to z values between 1 and 3. Function, or the integrand, is z times sine of x times cosine of y. Notice again that this function, z times sine of x times cosine of y, that's a function of 3 variables. It's continuous over the rectangular box B, where the x values are between 0 and pi, the y values are between 3 pi over 2 and 2 pi, and the z values are between 1 and 3. Because the function of 3 variables is continuous over the rectangular box, Fubini's theorem states that any integration order can be done and you'll have the same value for the function integrated over the rectangular box B. So in this problem, we're going to integrate with respect to z first, while we keep x and y constant. Then we'll integrate with respect to x, where we treat y as the constant. And then finally, we'll integrate with respect to y. So z times sine of x times cosine of y, the antiderivative with respect to z will be 1/2 z squared. And then sine of x times cosine of y is just constants. Evaluate the antiderivative at the upper limit, z equals 3, and the lower limit, z equals 1, using the fundamental theorem of calculus. So substitute in z equals 3 first. You'll have 1/2 times 3 squared times sine of x times cosine of y, which is 9/2 sine of x cosine of y. Subtract when you substitute in z equals 1. So you'll have subtract 1/2 sine of x times cosine of y. For the integrand, where you have the outside two integrals stay the same, 3 pi over 2 to 2 pi correspond to the y values, and the inside integral will be 0 to pi corresponding to the x values. When you simplify the integrand, you'll have 9/2 sine of x cosine of y, subtract 1/2 sine of x cosine of y. That's 8 divided by 2 sine of x cosine of y, or just 4 sine of x times cosine of y. And so now you integrate with respect to x, where you treat y as a constant. The antiderivative of 4 sine of x cosine of y with respect to x is -4 cosine of x times cosine of y. And again, use the fundamental theorem of calculus to evaluate the antiderivative. The values x equals pi for the upper limit and x equals 0 for the lower limit. Keeping the outside integral, which will correspond to the y values between 3 pi over 2 and 2 pi. When you substitute in x equals pi into the antiderivative, you'll have -4 times cosine of pi times cosine of y. Subtract -4, and you substitute in x equals 0, so you have cosine of 0 times cosine of y. For that cosine of pi is -1, so you'll have +4 cosine of y for the first term. And then the second term, cosine of 0 is just +1, and so you'll have also 4 times cosine of y for the second term after you simplify. So your integrand becomes 8 times cosine of y, and you integrate between 3 pi over 2 and 2 pi with respect to y. The antiderivative of 8 cosine of y with respect to y is 8 times sine of y, and then again use the fundamental theorem of calculus to evaluate at the upper limit, y equals 2 pi, and the lower limit, y equals 3 pi divided by 2. You'll have 8 times sine of 2 pi, subtract 8 times sine of 3 pi divided by 2. Sine of 2 pi is 0, so 8 times 0 will just give you 0, and then subtract 8 times sine of 3 pi over 2. Well, sine of 3 pi over 2 is -1, so you'll have -8 times -1, which will just turn out to be 8. And so that's the value of the iterated triple integral. And then again, because of Fubini's theorem, since the function is continuous over the rectangular box that we're integrating over, you can integrate in any order and you'll have the same value, which will end up with the value of 8. We did the integration with respect to z, then x, then y. If you integrate with respect to x, then y, then z, you also will still get 8. And you also will have the same value for any order of integration. So let's finish up this video by talking about some triple integral properties. It turns out that triple integrals have the same algebraic properties as double integrals and also single integrals, as stated in the following theorem. The theorem, which is properties of triple integrals, assume the functions f of x, y, z and g x, y, z. Both of these functions are integrable over a general region D. D sub 1 and D sub 2 are subregions of this general region D. Property number 1 says the sum f of x, y, z plus the function g x, y, z. This sum function is integrable, and if you want to evaluate a triple integral over the general region D for the sum of the two functions, you can integrate a triple integral for each function, f and the function g separately. So you can have a triple integral over the same region D for the function f with respect to v, plus a triple integral for the function g over the same region D. And you can just add the values for these triple integrals to find the value of the triple integral for the sum function. Property number 2. If c is representing a constant, then c times the function f of x, y, z is also integrable, and the property states that the triple integral over the general region D of the function c times f with respect to v, you can take the constant outside the triple integral and then find the value of the triple integral of just the function f. So the triple integral of the function f over the general region D, you can find out the value and then multiply your answer by c, the constant. Property number 3 says if you have a general region D, and you can divide the general region D into subregions, D sub 1 and D sub 2, where D sub 1 union D sub 2 is the entire general region D, the original region, and D sub 1 intersect D sub 2 is the empty set, so D sub 1 and D sub 2 do not overlap except possibly at the boundaries. Then the property says the triple integral over the general region D for the function f of x, y, z, where you integrate with respect to v, the volume, it's equal to a triple integral over d sub 1 of the same function, the same integrand, f of x, y, z, plus a triple integral over d sub 2 of the same function, f of x, y, z. So you can integrate over the smaller subregion d sub 1 for the same function, plus the integral of the same function over the subregion d sub 2. As long as d sub 1 union d sub 2 is the entire general region, the original one, and d sub 1 and d sub 2 do not overlap, except possibly at the boundaries, the sum of these two values will actually be the value of the triple integral of the general region D for the same function. Property number 4, if the function f of x, y, z is greater than or equal to a function g at x, y, z for any point that's in this general region D, then the value of the triple integral of the function f will be greater than or equal to the value of the triple integral for the function g over the same region D. And so finally, the next property for triple integrals states that if we integrate the constant function, where the function f of x, y, z is just the function 1, for all values x, y, z over the region D, then the property number 5 says the triple integral over the general region D for the function f, we're going to replace the function f, x, y, z with the function 1. Then you have the triple integral over the general region D of the function 1 with respect to volume. You will just calculate the volume of this region D. So this finishes our video on triple integrals. If you have any questions about any examples of this video, please let me know. Or if you have any questions while you work on homework for this section, please let me know that as well. And I'll see you at the next video when we talk about triple integrals over general bounded regions.